Hi, I'm June with episode 6 of Nibbles and Bytes. In this episode, we're going to talk about how to read the states of the 128's joysticks. In our hardware, the 8502 CPU has a limited number of input-output options available to it. As we've covered before, it has 16 address lines and 8 data lines for memory. But what else does it have? It turns out that the 8502 has a small number of general-purpose I/O lines that have been dedicated to cassette tape operation and detecting the state of the caps lock key. But that's it. In a machine with as many peripherals as the 128 has, the CPU has to rely on additional chips to get all of its work done. And this is where the CIA comes in. I didn't think I had any guests coming over.
Evening, ma'am. I'm Special Agent Zero of the CIA Cyber Terrorism Task Force. I'm here tracking a fugitive sprite wanted for theft of cycles, as well as potential attempted murder of a player sprite. I have reason to believe he's hiding here in one of your computers. May I come in?
Well, I suppose so. But wait a minute. My sprite's already been jailed. All right, let's talk it out. Okay, as I was saying, the Complex Interface Adapter, or CIA...
The same tool we use to capture rogue sprites?
Actually, that would explain why you're here.
That may be the case.
Okay, so let's talk this through then. The CIA is typically used for accessing peripherals like joysticks on the Commodore series of computers, because the CPU doesn't have enough general-purpose I/O pins.
Similar to how an Arduino or other microcontroller interfaces, except instead of being built into the silicon of the CPU, it's on a discrete chip, separate, providing access via memory map registers.
Right. Okay, let's get into more detail. Let's head to the whiteboard. The first thing we need to think about is how the CIA chips are wired to the various inputs of the 128. Each CIA chip has a set of 8 input lines, grouped together into ports, which can be read a byte at a time through the CIA registers. Confusingly, joystick port number 1 is connected to CIA number 1's port B. Each of the lines connected represents one of the 4 directions and the fire button. Joystick port number 2 is connected to port A the same way. Besides the joystick directions and fire buttons, there are 2 more pins in the connectors that are used for paddles. These pins are called pot X and pot Y and are connected to the SID chip rather than the CIA chips. These inputs aren't just used for joysticks though. The 128's keyboard is also wired into port B, which is why pressing the directions on a joystick in port number 1 will produce key presses like the space and the 2 character. Now that we know where the wires are connected, we need to know what happens electrically when a direction or button is pressed. Each of the switches in the joystick is connected from one of these input pins to ground. Internally, each of these input lines is also connected to a weak pull-up resistor that keeps the wiring at 5 volts. When a button or direction is pressed, the switch is closed. This causes the line to be shorted to ground or drain to 0 volts. Because of the resistor between the 5-volt source and the input line is there, this keeps the line from refilling with voltage and causing a wiring fault. Logically, 5 volts represents a 1, while 0 volts is a 0. So when we read the register, this means that if we see a 1, the switch is open, but if we see a 0, that means that the switch is closed and the user is pressing a direction or fire button. Now that we know how the joystick works with the CIA, we need to know how to read this information in our program. We'll use joystick port number 2, since we don't have to fight with the keyboard inputs at the same time. Each port is represented by a single byte value. Only the lower 5 bits in this byte are actually used or even connected. The top 3 most significant bits can be masked out and ignored. From least to most significant, each bit maps to up, down, left, right, and fire. Normally, since these pins are at 5 volts, each of these bits reads as 1s. Once the user presses a direction, they change to 0s. Note that even though the physical layout of the joystick prevents left and right, or up and down, from being pressed at the same time, electrically it's actually possible to press all 4 directions simultaneously. This is how some game glitches and cheats are discovered, so we should account for this when we make our game. Okay, I don't know if the sprite that I invented is the one that you're after, but I did develop a tool to capture him if he ever gets loose again.
Where is this tool?
Well, I have it right here. I call it the RetroPad. It works exactly like a joystick, except it gives you much more precision. You could say it's a more civilized tool for a more modern age.
But how does it work?
Well, let me show you. Let's write a short program to show the CIA registers in action. But first, we can use the memory dump command to actually watch the register change as we change inputs on the joystick. Now let's start on our visualizer program. Each time we press a direction or button, we want to indicate on the screen when that has happened in a graphical representation of the joystick. To get the state of the joystick, we first have to load its byte value into the accumulator register so that we can work with it. To actually test each bit, we use the logical shift right instruction, or LSR, to shift the least significant bit out of the A register and into the carry flag in the status register. From there, it's just a matter of using the carry bit branch instructions BCS and BCC to change the behavior of our program based upon the state of the carry bit. First, we should clear the screen of clutter, so our program starts by doing that with our very familiar screen clearing subroutine. The next major subroutine is our joystick checking loop. This is effectively the main loop of our program and pulls the status of the joystick while shifting through the bits. To keep things simple, each bit test is coupled with a separate subroutine to draw each component of the representation to the screen. The first thing our loop does is clear the representation off the screen. Next, it loads in the JoyPort2 status byte from the CIA register. From here, we start shifting bits and branching based upon the status of those bits. If the carry bit is set, or 1, we jump over the next instruction, which would draw one of the arrows on screen. The rest of the loop repeats this pattern for the rest of the bits that we care about, including down, left, right, and fire. Finally, we jump back to the beginning of the loop to start again. The next subroutine is the clear routine our loop jumps to at the very beginning. We don't actually clear the whole screen. This routine only overwrites the locations on the screen that we previously drew arrows on. Lastly, we have each of the very short subroutines for each part of the on-screen representation. Each of these loads in the appropriate screen code and stores it to the video matrix before returning. Okay, let's see this in action. See? Works really well, doesn't it?
Yes, much more precise than the other tools I have at my disposal. Do you have any software to go with it?
What am I, the CIA's Q?
Ma'am, you've been doing the country a great service.
All right. Okay, let's write a program to use the joystick's inputs and capture our sprite. Since this program is the most complex program we've ever written at the 128's monitor, we'll want to go over the overall design before we get to the code. The first part of this program is obviously the initialization routines. We have to prepare the VIC for sprites and colors. Once we've initialized everything, we enter our main loop. The first thing we do in the loop is delay. In this program, we're going to use the VIC's raster registers to synchronize our update rate based upon screen refresh rate. That way, movement on the screen isn't blazingly fast. Next, we move the sprite across the screen. Then we read the joystick register and update the jail sprite based upon which directions the user is currently pressing. The last thing we do is check to see if the fire button is pressed, and if the two sprites collide. If they don't, we go back to the top of the loop. Otherwise, we jail the sprite properly and halt the computer. Now that we know what we're writing, let's get into the code. The entry point to our program is fairly simple. The first thing it does is call into our init subroutine to set up the machine for operation. Next, it sets up the multicolor colors for sprites and characters. And finally, it jumps into the main loop. The init routine is much the same that we've seen in previous videos, so I'll go through it relatively quickly. Since we don't know what mode we're in, we disable BCD math before anything else. This is because we use the add with carry and subtract with carry instructions elsewhere in the program, and we don't want unexpected results. Like our previous programs that use sprites, we have to disable the basic interrupt handlers. Next, we set the VIC to read our custom character set at 2000 hex. The last setting for the character set is enabling multicolor mode. We start setting up the sprites by enabling sprite 0 and 1. Then we set the initial sprite position for both. The init routine has two more things to do before it finishes. Since we're animating the convict running, we have to set his initial animation frame. Lastly, we clear the screen using a subroutine we'll cover next. The fill routine is effectively the same clear screen routine we've used before. The difference here is that instead of filling it with only one hard-coded character code, this one allows you to specify the code as well as the color. First, it initializes Y as the counter for the clearing loop. Then, as before, we store A to the video matrix, address offset by Y. To set the colors, we transfer the color number from X to A and then store it in the color RAM in a similar way. The last bit of initialization before we enter our main loop is to set the various colors we'll be using. First, we set our sprite multicolors to black and white. Then we set sprite 1's color to light red, and enable sprite multicolor mode. The last bit of init code sets background colors 1 and 2 to orange and brown, respectively. Now that we've initialized the system, we can get into our main loop. We'll split this into two parts so that we can cover it more easily. The very first thing we do is read the VIC's sprite collision register and throw away the value. We have to do this every frame because it operates like a latch and will retain its value even after the sprites are no longer colliding. By reading the register, it automatically is reset to 0. Next, we delay our loop until the VIC has painted a full screen. This is done in a delay subroutine we'll cover later. Once we've synced up with the refresh rate, we can call the routine that makes our convict run across the screen. Once we've moved the convict, we can then poll for the current state of the joystick by loading the value at DC 100 into A. Like the joystick jail program we wrote earlier, once we have the joystick state, we shift through the bits in A and skip over the JSR instructions to update the jail position on screen. If the bit is clear, or the user is pressing on the joystick, then we jump into either the move horiz or move vert subroutines to update the jail position. The last bit of our main loop only has two more jobs before it restarts. Before jumping back to the top, the loop checks to see if the fire button has been pressed. If it has, then it jumps into the sprite jailing subroutine. Lastly, it animates the running convict with the animate subroutine. The next and suddenly important routine is the delay routine. This effectively stops the CPU from changing anything while the VIC is drawing the screen. First, we load in the VIC's raster line register into A. This effectively just tells us which line the VIC is currently drawing to the screen. Next, we loop back to the load instruction until the value reads 0. Once it does, we know that we can continue executing without causing visual artifacts like tearing. Since we might want to delay several frames, this routine also includes an outer loop to wait repeatedly based upon the value in the X register. Now that we have our delay in place, we can concentrate on the main behaviors of the program. The first of these is moving the convict across the screen. Since we're using the add with carry instruction to move the sprite's X position across the screen, we clear the carry bit so we don't accidentally add too much. Next, we load in the sprite's x-coordinate, add 3, and store it back. Since we're using the ADC instruction, if we overflow, the carry bit will be set. If it's clear, then we can simply exit the routine. If the carry bit is set, however, we need to update the sprite x MSB for sprite number 1, which is what the rest of this subroutine does. Now that we have the convict moving around, we need to give Agent 0 the ability to capture the sprite by moving the jail. We'll start with the vertical movement, which is easy. The first thing we need to do is save A to the stack, since we end up clobbering it in this subroutine. Next, we load in sprite 0's y-coordinate. If the carry bit was set by the caller, then that means that we're planning on moving down the screen by adding values to y below. Otherwise, this subroutine subtracts 8 from the y value and jumps past the addition. Once the arithmetic is finished, we store the new value back to the sprite coordinate register, pull the previous value of A from the stack, and then return. Now that we have a handle on vertical movement, let's tackle horizontal movement. Like we did before, we save A to the stack. This is so we don't have to reload it from the joystick register again after calling this routine. Once that's done, we can load in sprite 0's x position. Like the vertical movement routine, we'll use the carry flag to determine if we move left or right. If it's set, we jump to the addition part of this subroutine. Otherwise, we fall through to the subtraction. Now let's cover the subtraction part of this routine. Since we're moving left, we set the carry bit, subtract 8, and store the result in the x register. In this case, if the carry flag is still set, we know we didn't overflow and that we can exit the routine. Otherwise, we need to update sprite 0's x MSB register. The addition part of this routine is very similar to the subtraction part. In this case, we clear the carry bit so we don't add too much. Then we add 8 and store it to the sprite 0's x register. Like before, if the carry bit is still clear, we know we haven't overflowed and can simply exit. Otherwise, we need to adjust sprite 0's x MSB register. Like the vertical movement routine, there is still some additional work that always needs to be done before we return. Since we pushed A to the stack, we must be symmetrical and pull it from the stack before returning. Now that the hard part is done, we can give our convict some animation in the animate routine. We want our sprite to move a little before we change frames, so we load the sprite 1 x coordinate and skip the animate routine every 4th coordinate. If it's time to change frames, we simply increment the sprite 1 pointer directly. We then load in the maximum pointer number for our animation set into A and compare to what we just stored. If the pointer is not equal, it means we haven't reached the last sprite in the animation, so we just return. Otherwise, we set the pointer back to the first frame in the animation. At this point, we can animate the convict and move the jail, so now it's time to write the jailing routine. The first thing we have to do is load in the sprite-to-sprite collision register from the VIC. If sprites 0 and 1 have collided, the 0th and 1st bits will be set, so we compare against 3 here. If these 2 bits are set, then we branch into the actual jailing code. Otherwise, we return here. At this point, the fire button is pressed while the 2 sprites have collided, so now we need to fill the screen with bricks in a light red color using our fill routine. We then cut a window in the bricks so that we can see the sprites with a different background. We'll cover this routine in a moment. This next chunk sets the position of the 2 sprites to the center of the screen, inside the window. Finally, we set the convict sprite shape to the jailed one and do an infinite loop back to the same location forever. Now it's time for our last subroutine, the window clear. Rather than trying to formulate a loop to clear a specific part of the screen, we can instead have the kernel do the work since we're on a 128. clearing a region of the screen is a two-part operation. First, we have to define the window to clear, and then we have to clear it. First, we set the coordinates for the top left corner of the window in A and X and call jwin with the carry bit cleared to set it. Next, we set the coordinates for the bottom right corner of the window in the same two registers and call jwin with the carry bit set to set it. Once that's done, we can call the clear routine to actually clear the window. Phew! Okay, now that the program is written and entered, we just need to load in our sprites and character set. And now we can let her rip!
Yes! Ha! This isn't the sprite I was looking for, but I will need to confiscate this for my hunt. Thank you again so much for your help. I will, of course, have to confiscate this. But don't worry, the country thanks you for your service. Have a good day.
Don't you want version 2? Ugh. Thank goodness he's gone. Such a pain. Okay, so at this point, we've covered just the joystick functionality of the CIA? Okay, good. Anyway, these chips are responsible for more than just keyboard and joystick input, and include additional functionality we didn't get into yet, such as clocks. In the next episode, we'll be covering the Buddy Assembler system, since our programs are becoming more and more complex, and we're delving deeper into more complex topics soon. As always, I'd like to give a shout out to all my patrons. If you'd like to join them in their patronage, you can do so in the Patreon page in the description below. And with that, thanks for watching, and see you in the next episode.
Damn, that was palpable. Wow.
See? Works pretty well, right?
Yes.